Okay, I guess maybe we can start. So welcome to 130B, Quantum Mechanics. Today we are going to continue the discussion of second quantization, which is about how we represent identical particles in quantum many-body physics. So maybe first let me recap that in quantum many-body systems, we want to describe systems of many particles, and the first way we describe it is when the particle is distinct, then we basically use the idea of tensor product to describe the state of the system, because when the particle is distinct, you can basically label, or you can ask what is the state of the first particle, the second particle, and then you put their state together and tensor product them into the system state. So that's the idea, and that's the notation there. So every time we use a sequence to denote the state of a many-body system, but in systems where the particles are identical, this is no longer a good language. So last time we basically mentioned this idea that in first quantization we need to specify the state of each particle, but in second quantization we only want to specify how many particles are there in every state, because there's no way to distinguish what the first particle from the second particle, so it doesn't make sense to ask, for example, what is the state of the first particle. So given that, second quantization takes a strategy of using this number representation. Instead of talking about the state of each particle, we talk about the number of particles occupying each state, and that's the idea. So that's why we introduce the so-called occupation number basis, which instead of using a sequence of states to describe which state the particles are in, we use a sequence of numbers which describes how many particles are there on each state. But this number representation basically is still made of the first quantized language, meaning that, for example, if there's one particle in alpha, one particle in beta, then the quantum state is basically a linear superposition, actually an equal probability linear superposition of the first two cases, where you basically perform all possible permutations of these particles and then try to symmetrize or anti-symmetrize their state vector or their wave function. And for identical particle, the essential idea is that the probability distribution of the system is invariant under permutation or under exchange. But we know that the exchange has only two possibilities. If the probability is invariant under exchange, then we can either under exchange there's no minus sign or there's a minus sign. So that leads to bosons and fermions. So last time we basically start talking about the relationship between the occupation number basis and the first quantization language. So we want to build a connection between the second quantized formulation and the first quantized formulation in terms of their basis. In second quantized formulation, we talk about these numbers. So for example, we look at this example. If we have one particle in alpha, one particle in beta, then that in first quantized language, you can first write down a representative state. The representative state is you assume that the first particle assumes the alpha state and the second particle is in the beta state. Of course, we know if you only write down a term like that, that term will not be symmetric under permutation, because now if you exchange first and second particle, you basically exchange their state labels, then that leads to a different state. Then the strategy then is to symmetrize the system, meaning that you take this possibility and that possibility, you add them together and divide it by 1 over square root, basically the number of terms you have there. That's basically symmetrization. In that way, we create a new state, which is a linear combination of the previous states, all possible permutations, and then every permutation appears with the same probability. So it becomes very crucial to determine the sign here, because in terms of probability, both this expression and that expression, they have the same probability distribution. If you want to talk about probability, you need to take this coefficient and then squared, and both of them correspond to half and half probability combination of alpha beta and beta alpha. But then we know in quantum mechanics, it's not only about probability, it's also about probability amplitude, which is like a square root root of the probability. And because of this square root, there's a plus minus sign ambiguity. And this sign ambiguity, most importantly, the relative sign ambiguity between these two terms are the most important, because the overall sign, anyway, doesn't matter. It's any quantum state you can change it by an overall sign, but this relative sign is very important. It's something physical. And then this relative sign basically tells you when you exchange two particles, what should be the sign that you obtain. If you obtain no sign, that is like a bosonic system. If there's a sign associated with each exchange, then that's a fermionic system. So that's the basic principle to rewrite the second quantized spaces, which is in terms of the particle number, occupation numbers, to rewrite that in terms of linear superposition of first quantized spaces. Okay, so that establishes a connection. Okay, so there's also other examples here, like if you have two particles in alpha, one particle in beta, the strategy is always first write down a representative state. For example, I assume that it is alpha, alpha, beta, and then I can enumerate all possible permutations. And then for bosons, I need to sum the permutations together. And then for fermions, I need to sum the permutation together with a minus sign, and the minus sign determined by the permutation sign. The permutation sign is a sign structure which counts how many exchanges have you done in the permutation and calculate the parity of the exchange. So it depends on whether it is an odd number of exchange or even number of exchange. If there's an odd number of exchange, there's an odd number of, this sign is odd, basically. And then last time we also explained that it doesn't matter how do you count the number of exchange, because the number of exchange can differ by 2, but the parity is never changed. So okay, so this is the basic, this is the final formula we end up with, although it looks a little bit complicated, but the idea is what I described just now. Whenever you want to translate a second quantized basis state in terms of the occupation number, where this board phase n basically is a sequence of numbers which describe what are the occupation number for this alpha state. So you first need to construct a representative state by copy this alpha state n times. And then for this alpha, you tensor product all the possible alphas through all possible states. Like the first state, copy n alpha n1 times, the second state copy n2 times, and so on. You just tensor product all these together to make the representative state, and then you apply the symmetrization operator, where the symmetrization operator is try to permute these representative state, and then summing over all possible permutations. In the end, we need to normalize the state as we required. And then for fermions, it's the same idea. You anti-symmetrize the representative state. So this is how we construct a bosonic second quantized state and fermionic second quantized state. Both are labeled by the occupation number. Okay? Any questions? So that's what we have learned so far. And today we are going to not only talk about these bases. Now today we want to define some operator which can operate on these basis state. For example, a very important operation that we need to discuss in second quantization is how to add one more particle or remove one more particle from the many-body system. Because you can see it's all about particle occupation numbers, so we want to know how to change them. And then the way to modify the particle number is by applying the so-called creation and annihilation operators. Creation operator, according to its name, creates or adds particle to the system. Annihilation operator removes the particle from the system. So that's what the name indicates. But in order to understand that, we need to first define them and then understand how they operate. And before defining the creation annihilation operator, I want to talk about how to insert and delete a single particle state from the first quantized representation, following a manner which is either symmetric or anti-symmetric. So let's first make some definition. So first of all, let's assume that this alpha and beta, when I write alpha, beta in this small font, Greek letters, and then they correspond to the so-called single, they correspond to labels of the single particle state. and then that 1 be the tensor identity such that 1 is like, you should really think 1 is like a 1-by-1 matrix. So its identity under tensor product, because any vector, no matter how long it is, if it tensor with a 1-by-1 matrix or 1-by-1 component vector, it's still the same vector itself. So we can also define this tensor identity, and then but when I write this capital psi or capital phi, these correspond to the generic first quantized state. The generic first quantized state is something like a tensor product of a bunch of single particle states and then linear superposition with each other. So that's the generic first quantized state. So we want to know, like, for example, this generic first quantized state already contains n particles. Now I want to add one more particle to the system. Then I will obtain a new state which contains n plus 1 particle. So n particle means that if you decompose this state into this tensor product of alphas, there are n single particle states tensor product together. So now I want to add one more particle, meaning that I want to tensor another single particle state to each one of these basis states, for example, in this many-body system. So let's see how it works. In order to define that, we need to introduce something called insertion and deletion operator. It is not creation and annihilation yet, but it is already very close, the idea. So the insertion operator, I use a triangle to denote that. The idea of this triangle is like pushing the state into, so if you take a single particle state, you want to insert that into a many-body system, you push that into. And then there's a plus minus sign as a subscript, which describes when you insert the single particle state, whether you want to insert it in a symmetric manner or anti-symmetric manner. Symmetric and anti-symmetric refers to the symmetrization and anti-symmetrization of the many-body wave function of the many-body system, right? It corresponds to either bosonic many-body system or fermionic many-body system. Because when you insert, you basically need to insert the state at every possible positions. And then that leads to permutations. And then because of the permutation, we need to take care about this plus minus sign. Let me first talk about the last relation, which is the very important definition of how to insert. Suppose I have a alpha single particle state, which I want to insert into a many-body system, where the many-body system has basically is a tensor product of a bunch of states. But you don't need to worry about this complexity. You just assume that this tensor product, in any case, starts from the first state and tensor product of the remaining states, right? So what I only need to do, I only need to define is recursively define how do I insert, how do I push this single particle state into this tensor product of many single particle states. So you first need to, for example, put this alpha in front of everything. That is one possibility because for example, this guy already have n object, n state tensor together. If you further tensor alpha state, it is n plus 1. It has n plus 1 particles, and then the newly added particle is indeed in this alpha state. So if you want to add a particle in alpha state to the system, that is what you need to do. But we know if you just simply do that, we are violating the principle of permutation because this alpha is only added to the front of the sequence. And then we know that in this many-body sequence, when systems, when particles are identical, there's no way to distinguish different ways of ordering the elements in the sequence, right? So we also need to consider the case where this alpha is not added to the front, but it is added to the places which is behind beta, for example. So you can define this by saying that if you want to insert alpha to beta, what you need to do is I first put it in the front and then put it in front of beta or put it behind beta. And then because in front or behind beta requires you to exchange alpha through beta. So there's a relative minus sign between these two terms. So that's the way to define the insertion. When you insert new state, it is like adding to the front or adding to the second place. When you add to the second place, this alpha will further act on whatever that is inside. So this psi will further expand into a sequence, and there's also a first token or first element in the sequence. Now this, you need to apply this recursion relation to this part, and then you further put alpha in front of that, or alpha through the next token. Okay, so that's the idea. So if you really have a sequence like beta 1 tensor beta 2 tensor beta 3, and then when you insert this alpha plus or minus into this state, you basically do alpha beta 1 beta 2 beta 3, and then plus or minus, depending on this plus or minus sign. Suppose I use the minus sign, then the first time I need to exchange to here, it goes like beta alpha, beta 2, beta 3. And then it further move alpha to the next place, it goes like beta 1, beta 2, and then alpha 2, beta 3, and so on, right? So you just keep applying this recursion relation to insert this alpha state to the sequence. And then it guarantees, this recursion relation guarantees a way that, first of all possible places that the alpha can be inserted will be enumerated through this process. And secondly, every time you go to a new places to insert alpha, you will automatically carry this relative minus sign with respect to the previous one. For example, this one also has a relative minus sign with respect to this one. But this one already have a minus in the front, so this becomes a plus in the front. But that's indeed what we require, because in order to calculate the relative sign between the third term and the first term, they are indeed differ by 2 exchanges, which is so their relatives. The first term and the third term has a relative same sign, even for fermionic system. So for bosonic system, it will be very simple. You just need to add all of them together. It's a symmetrization. So that is labeled by this plus. And then for fermionic system, we need to take care of this minus sign. Okay? So that's the idea of adding a new state into the existing sequence of single particle states. Okay? Any questions? And then we will also need to define something like deletion, which is removing or take out a state from that existing state. So for example, this is an n-particle system. You want to take out the alpha state. But then there's a subtlety. It is just like you want to delete, it's like an RNA sequence, basically. So this sequence is like a sequence of these tokens in biology, like RNA. We also have this nuclear site that forms a polymer. And then at every place, there's basically 4 different choices, A, U, C, G. And then basically, biologists knows how to add this nucleotide to this sequence. But here, for example, if you want to delete it, in biology, what happens is that you need to first search. You need to first find where are the, for example, I want to delete an A. And then where is the A in this sequence, right? The sequence may contain many different A's, or maybe it doesn't contain any A in this AUCG sequence. And you need to first find it. And in biology, how people find it is, it turns out, due to the chemical properties, A and U, they are conjugate to each other, and C and G, they are conjugate to each other. So if you somehow send in a protein which carries a U base, and then it will match up with the A base, and then cut it off the gene, basically, cut it off the RNA. So there are processes like that. So it is very similar that in physics, we are going to do the same thing. If you want to delete a state alpha, you first need to find it. How to find it? You first need to compute the inner product, because this inner product or scalar product describe whether the particles are, whether the 2 states are identical or distinct, right? If alpha and beta are identical, then their scalar product will be 1. If alpha and beta are distinct states, meaning that they are orthogonal, then this scalar product will be 0. So, suppose, so this is basically a searching problem. This alpha is like the conjugate genes. This beta is the genes that you want to check. And then you calculate their scalar product. It's like trying to matching these two bases. And then if they match, meaning that if the scalar product is 1, then you know that this is the target you want to remove, and then you basically take this factor away. Because once alpha and beta matches, then this whole factor reduces to a single 1. And then that means in the remaining state, there's no longer this beta factor in the front, right? So I have successively removed the single particle with beta state from the remaining sequence by this operation. However, if beta does not match alpha, then this scalar product in the front will be 0. That means this state will no longer appear in the linear superposition, will not contribute. So it is like a failure. You try to search for alpha, but this beta doesn't match alpha, so the first token doesn't match. Then you need to move on and search for the tokens in the later sequence. But this first token doesn't match, so you can't delete that token from the sequence. So basically, you don't have this contribution of this kind of terms. And then instead, you need to move on to the remaining sequence. That means you basically need to switch place between alpha and beta. So you keep beta because beta now is safe, right? Beta has passed the exam that it is not matching alpha, so it's not going to be deleted. So alpha will move on to seek the places to make the deletion in the later sequence. So this becomes a recursive relation. So you also notice that in this recursive relation, we basically use two ideas. One is we use the scalar product to do a search. The scalar product has this nice property that it equals 1 when it matches, when it equals 0 when it doesn't match. So it is perfect property for us to do this search. And then secondly, we also notice that whenever we take alpha through beta, we need to be careful about this plus minus sign, which is actually specified by the subscript of this deletion operator. This deletion operator not only just delete, it also carries a plus minus sign to indicate whether when I exchange this when I move this deletion operator to the next place, whether there should be a relative plus or minus sign between these two terms, basically. And in that way, this deletion operator will also satisfy. If you follow this sign rule, you can show that if you start from a bosonic state, after deletion is still a bosonic state. If you start from a fermionic state, after deletion is still a fermionic state. Okay, so that's the idea. And then this alpha beta, as I said, assuming alpha and beta are labeled orthonormal bases, so they automatically have this scalar product being delta function. In this discussion, we always assume that alpha beta are orthonormal bases. The single particle states are labeled by the orthonormal basis labels. So we never encounter the case where the scalar product is between 0 and 1, for example. So the scalar product here is always 0 or 1, given that alpha labels the basis state. Okay, so that is the very essential, the most crucial part of the rule are these recursive rules. And apart from these rules, we also, for mathematical completeness, we also need to define some other auxiliary or some other rules that helps us to make it a complete algebraic system. That is, first of all, we need to define if you alpha add on the tensor, which is the tensor product identity, what happens, because tensor product identity has a property that a tensor product with any state is the state itself, so it doesn't matter whether you add it from the front or add it from the back, it's also always the same state. So we can define that when you insert alpha state to this identity, to this 1, 1 actually corresponds to the vacuum state. It's like there's no particle. So this is called vacuum property. And when you add one more particle to the vacuum, then the many-body state is simply the state of that particle you add to the vacuum. But if you try to take one particle from the vacuum, then the result is 0. Because if you try to take the particle from the vacuum, you do this search, right? During this search, you never have any chance to find a state in the vacuum which matches your single particle state. So the search will fail in the end. And then when you fail, that means all this alpha, beta in the product will always be 0. You never get any non-zero in the product from the search, then the answer is 0. So that's why if you try to start from a vacuum state and you try to delete any single particle state because nothing exists in vacuum, so the result will just be a 0 vector. This 0 corresponds to a 0 vector in the many-body Hilbert space. Okay? And then there's also some more nicer to understand property, which is the linear property, which basically say that the insertion and deletion operator, they really forms a linear operator that if you want to insert alpha to a state which is already a linear combination of psi and phi, then what you need to do is you basically insert this alpha to psi and insert alpha to phi, and then don't care about this superposition. You can first insert and then superposition. It will be the same as first superposition and then insert. The same applied to deletion operator. That it's basically because it's a linear operation, so you can do that operation and then linear combine, that will be the same. So that's called the linearity, okay? So these two are the easier properties. The most important one is this recursion relation. That means when we want to insert, we need to start from the first place and then keep moving on. And then every time we move on, every time we cross another single particle state, we need to be careful to attach this plus or minus sign depending on whether we are talking about a bosonic system or a fermionic system. And then when we do the deletion, we also need to take this alpha and then compare with each one of these existing betas. And then when it matches, then the term, for example, this alpha 1, alpha matches beta 1, then there will be a term of beta 2, beta 3. That is as a result of this matching. And then you keep comparing alpha with all these betas until you exhaust all the tokens in this sequence, okay? So that's the rule. Any questions? Yeah, very, very similar to this RNA deletion idea. We need a conjugate. We need a conjugate state to do this checking or this matching, okay? Okay, so with this general rule in mind, we can talk about very specifically about the boson creation and annihilation operator. It is really just insertion and deletion other than a factor. So you can see it's already the same thing. So this factor, we will explain that later. This factor is there because to ensure certain normalization. But the idea is that the boson creation operator, which is denoted as an operator, so a boson, we use B to denote a boson, and then operator, we use a hat to denote its operator, and then we use this alpha to label the fact that this boson creation operator is adding an alpha state to adding one more boson, which is in the alpha state, to the system. Or another way of saying, this boson creation operator is trying to increase the occupation number of the alpha state by 1. So that's the idea. And then the way to do that is to take this alpha state and insert into whatever state you want to act on. And then when you do the insertion, you put a plus sign here to indicate or to remind yourself that it is a bosonic insertion. It's a symmetric insertion. Every time you exchange through a new tensor factor, it has no sign accumulation. And then after all these operations, you divide everything by 1 over square root n plus 1. The reason for this factor is because if you try to count how many possibilities can you insert alpha into the psi state. Suppose psi is the n-particle first quantized state psi. So that means this psi will be a linear superposition of a tensor product of a single particle state like that, right? And then by saying it's an n-particle state, meaning that there will be n-particle, n such beta 1, beta, for example, this is a 3-particle state. Already 3 of them existing in psi. Of course, psi can be a superposition of these 3-particle states, but for every basis state, it's 3-particle. It's, for example, like that. So now, if I want to insert alpha into this sequence, there are 4 different places that I can insert. I can insert it here, 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 right? So alpha can be inserted in n plus 1 different places if psi is an n-particle state. So that's the idea. And because there are n plus 1 different possibilities, if you run this recursion relation will automatically generate n plus 1 different terms. Okay, some of the terms may be maybe the same, but that doesn't matter. Altogether, there are n+1 terms. So the idea is to linearly combine them in a way that this is still normalized. So that's why you wish to take 1 over square root n+1 in order to combine them. So that's the rule. So yeah, just stick to the rule. That's the definition. That's how people define creation operator for bosons. Basically, insertion followed by 1 over square root of the number of possible ways to do this insertion. Number of possible ways, 1, 2, 3, 4, to do the insertion. And the deletion operator, so annihilation operator is also just deletion operator followed by 1 over square root of number of ways to do the deletion. For example, B alpha, which is annihilation operator, which annihilates a boson in state alpha, which means it reduces the occupation number n alpha to n alpha minus 1. So when it acts on an n-particle first quantized state, it basically acts in this way. It basically tries to first do a search and try to match, and then when it matches, then it removes the corresponding single particle factor in that state. And then it do all these kind of matches, and then how many possibilities you can remove alpha from these 3-particle states, for example. So suppose I have a 3-particle state labeled by beta 1, beta 2, and beta 3. Then I first need to compare alpha with beta 1. If that matches, then basically I got this term. Or I try to match alpha with beta 2. If that matches, I got beta 1 times beta 3. If alpha matches beta 3, I got beta 1 times beta 2. So you have basically still 3 different possibilities. Either you remove the first one, or you remove the second one, or you remove the third one. I don't mean simultaneously remove them. I mean there are 3 possibilities to remove a single particle state from a 3-particle state. So if you want to do this removal, basically, if suppose all beta 1, beta 2, beta 3 are equal to alpha, then basically there will be 3 possibilities, and then the 3 possibility will be that's why we need to linear combine them with 1 over square root of n. These 3 possibilities actually is n possibilities in general. So you may wonder that sometimes they don't match, and then I got a 0. So the rule is that you don't need to care about whether that's 0. You just need to count in general, what are the possibilities. You don't need to specifically look at whether certain terms 0 or not. It's not counting the terms that you have. It's counting the possible ways. So this 1 over factorial, 1 over square root something, this something is always counting the number of ways to do deletion. This is counting the number of ways to do insertion. If you have n particle, you have n+1 different places to insert. And then if you have n particle, you have n different places to do deletion, to remove, right, to delete. And then that's why there's these factors. So that's the rule. And then I secretly already using dagger here, meaning that I'm actually implying that these 2 operators defined in this way are Hermitian conjugate to each other. Actually, if you don't have this factor in the front, the insertion and deletion operator by themselves are not Hermitian conjugate to each other. But with these factors, actually they are Hermitian conjugate to each other. And then it is not obvious, I haven't proved that, but just bear with me that this is the way that people define creation and annihilation operator. I think in the following example, we'll see how this rule works, and then it will give us more intuition. Okay, any questions about the general rules? Yeah, so now let me talk about a very specific example where suppose based on this definition, we can show how creation and annihilation operator on a single mole, acting on a single mole Fock state. What does that mean? We know that the Fock state basically is labeled by the sequence of occupation numbers. But let's consider a single mode Fock state, which means in the whole system, there's only one possible single particle state, which may be just labeled by alpha. There's only one state that can be occupied. So all the possible states in this many-body system are just labeled by the occupation number of that state, which is denoted as n alpha. So we want to show that by defining the creation, boson creation and annihilation operator as above, as we described previously, you can show that when you apply this boson operator on the n alpha state, it goes to n alpha plus 1 with a factor, square root factor in the front. Maybe you are already very, it looks very familiar, right? It is actually the creation and annihilation operator we learned before in harmonic oscillators. It's precisely the same thing. But but previously we start from quantum bootstrap and all those kind of things, and then just define this creation and annihilation operator as position and momentum operator, right? So for example, maybe you still remember in harmonic oscillator, annihilation operator is position plus I momentum operator divided by square root 2. And then we rely on the algebraic property between position and momentum operator to define these operators. But now, in today's lecture, we are starting from a completely different idea. We start from the discussion of a many-body system, which is boson, and then we talk about its first quantized wave function, and we talk about how to insert a new particle into the system, and we through that kind of idea to describe or to define a creation operator. Let's look at the creation operator. So if you want to start from a creation operator acting on an NA particle state, which means, so N alpha. So that means this state means that the alpha single particle state need to be tensor product n times, which correspond to this one, alpha tensor n times, basically. So all together, this n alpha times. So that is the state of n alpha state in the second. So on the left-hand side is the second quantized language. Right-hand side is the first quantized representation. They come in correspondent to each other. So the idea is, if you want to write down the representation for this state, you first write down a representative state. You can treat this as a representative state. But this representative state is also very special because this state itself is already permutation symmetric, right? No matter how you permute the particle label, it's not going to end up with a different state. So in the end, after symmetrization from this representative state, you will have many of these, the same state adding together, but that adding together will only contribute the overall factor in the front. But that factor is still not important because after normalization, this state is supposed to be of norm 1, and then this state is also supposed to be of norm 1. So the only way for them to be equal is that they just equal to each other directly. That's why this n particle state is represented as these multiple alphas tensor product together, which I use this power notation to denote this tensor product. So now I want to insert a new alpha into this. And then there are how many different ways I can insert it here, 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 here. There are n plus 1 different ways. And then no matter where I insert this alpha, I will just make this sequence longer, right? This sequence already contains n alpha of alphas. And then I will just make it n alpha plus 1 of alpha, of these alphas product together. So first of all, the tensor factor will be n alpha plus 1, meaning that the number of alphas will have one more. There will be one more alpha inserted into the sequence. And then how many different sequences in the end I obtain, because following the iteration rules, if I want to do insertion, I put it in the first place, and then plus the result, I put it alpha in the second place. So how many of them? There are n alpha plus 1 of them, right? Adding all together, so that leads to this state multiplied by this factor. But remember, when we define the creation operator, we also already define a 1 over square root n to normalize things. So in the end, the factor is just square root of n plus 1. Nicely matches the numerator, nicely matches the denominator, such that there's instead of divided by square root of n plus 1, it's actually multiplying square root of n plus 1. And then for bosons, if you want to do annihilation, that's the same idea. You annihilate from this sequence, and then after annihilation, this sequence will only contain n minus 1 different alpha states. But how many possible ways can I do that? I can annihilate alpha from the first place, second place, and so on. There are n alpha different possible possibilities. So again, the numerator nicely matches the denominator, and then the resulting factor is just square root of n alpha in the front. So from these two derivations, although it's in the exercise, but I think it's very helpful to show you that just following these rules, and then we can define this creation and annihilation operator in a way such that when it acts on the n-alpha state, its behavior is completely the same as the harmonic oscillator, as the creation and annihilation operator we define in the harmonic oscillator. And specifically, if you look at these examples, if you try to create a particle boson in a zero particle vacuum state, you get a one boson state. But if you try to annihilate that on the vacuum state, you basically get a zero, the zero factor. Okay, and then from this discussion, we can also calculate, for example, try to look at B dagger B, this operator, and then suppose we apply B dagger B on this n state, just following these rules. You no longer need to go through all these tedious details of how to insert and delete. Once we know on the very high level that there's these algebraic rules, you can just apply that and show that it basically B dagger B acting on the n particle state, it gives you n particle state with a factor in the front. This equation means that this n particle state as a second quantized basis state is actually an eigenstate of this operator B dagger B. So the B dagger with an eigenvalue exactly matching the number of particles in this n particle state. So that's why B dagger B is the particle number operator. And then this is a particle number operator that specifically counts the number of particles in the alpha state. Because B dagger B only acts on these alpha states, right? It's only responsible to insert alpha state and to remove alpha state. So, so for another beta, it has its own B dagger B number operators. Okay. So furthermore, just as we previously discussed in harmonic oscillators, you can start from the vacuum state and keep using creation operator. Apply the creation operator n times, then you can raise the vacuum state of alpha to the n particle state of alpha state. Okay, so all of this is the discussion of a single mode Fock state, which means we are focusing on the unique, only single mode in the system, which is alpha, which we call it alpha. And then we can generalize it to multiple modes. For example, if you have a system which has multiple modes, which maybe we call the alpha, beta, gamma, and so on, and then the second quantized state will be labeled by the occupation number on each of these states. And then if you want to apply now a bosonic operator, a boson creation operator, specifically creating one more particle on this alpha state, then what happens is that this state, first of all, the number of particles will get increased by 1. Secondly, very importantly, there's also a prefactor, and the prefactor has to do with the number of ways that you can insert this alpha state into that already existing n different alpha particles, right? You can, the number of ways you can add one more alpha particle to the existing alpha particles. There's n alpha plus 1 different places for you to do this insertion. And then for annihilation operator, first of all, you decrease the number by 1, but also you need to multiply with the square root of the number of different ways to do deletion, which is n alpha in this case. Okay, so these are the defining relations of boson creation and annihilation operator. So in this definition, you can generalize it to any alpha. For example, if you, instead of creating on alpha, you're creating on beta, or annihilate on beta, it's the same thing. You just need to plus or minus this number by 1, and then multiply the corresponding prefactor, which is now becomes n beta plus 1 square root, or n alpha, n beta square root. Depending on the label, okay? So with that definition, if you are given this definition, we can further derive that there's actually a set of commutation relation between these beta and alpha creation and annihilation operators. So these are the boson creation operator that creates boson on the beta state. These are the boson annihilation operator annihilate boson on the alpha state. So you should think that there are, if you have d number of different states, there are d number of annihilation operator and creation operator. They forms a set of operators which you can compute their commutation relation, and their commutation relation is like if they are both creation operator, they commute. If they are both annihilation operator, they also commute, which means if you want to keep creating particles, it doesn't matter the order that you apply this creation operator. You can apply creation operator in arbitrary order you wish, as long as you are keep applying creation operator, or you are keep applying annihilation operator. But if you apply creation and then annihilation, then the order matters, because there's a difference between B dagger B and BB dagger, which is basically what we have already seen previously in, for example, in harmonic oscillators, okay? So all these algebraic relation, you should treat this as a definition of boson creation and annihilation operator. So instead of, so there's two definitions. One is the operational definition. The operational definition of creation and annihilation operator is just define it on the first quantized level, and then how to insert and remove states, right? And then there's also a higher level definition. You can call it the second quantized definition, which is defining these operators by their commutation relation. It's actually true that as long as any operator, any set of operators satisfy this algebraic relation, they will have exactly the same effect as boson creation and annihilation operator. As if there is indeed a many-body system, quantum system, where you can really annihilate, or you can really add or remove boson from the system. So that's why originally when we start from harmonic oscillators, well, there's no idea of bosons, no ideas of particles. But when we follow the derivation, when we show that we can define operator in this harmonic oscillator system and satisfy this algebraic relation, we automatically give rise to the emergence of bosonic excitations in those systems, which is what I want to say here. And so maybe in the last 4 minutes, let me also quickly go through fermions. So fermions actually is much more simpler than bosons, although it has this minus sign. But the nice thing is that its occupation number can only take 0 or 1. So it's, the rules are very simple. For the fermions, it's also the same. When you want to create fermions in a many-body state, you need to do you can see it's exactly the same, kind of expression, other than you replace this plus to minus, because the only difference between fermionic state and bosonic state is whether fermionic state is anti-symmetric under permutation, bosonic is symmetric, so you need to take care of this anti-symmetric exchange minus sign for fermions. So for fermions, the creation and annihilation operator we denote it as a C, C alpha. Dagger is creation, and no dagger is annihilation. Annihilation is also defined this way. So by following this definition, we can very easily check that fermion, the only difference is that because the fermion operator can only have n alpha equals 0 or 1. So instead of creating on n alpha, instead of taking it to n alpha plus 1, actually it takes it to 1 minus n alpha. The reason is that this n alpha is only, for example, this n alpha is 0, then it basically takes it to the 1 state. But if it is 1, it basically need to annihilate the state, which is the idea here. If you start from the n alpha is 0, then basically you're adding a single particle to the vacuum state. Then that will be that single particle state, right? That means alpha will be occupied by one particle. But if you dare to further add another fermion into the system, then you are attempting to do something like this. But that leads to, because if you want to make an insertion with a minus sign, right, you need to insert it in the first place, insert it in the second place, and then take a difference between these two states, and the difference between these two states is 0. So when you apply further apply a fermion creation operator on a state which already is occupied by a fermion, then there's no such a possibility because of Pauli exclusion that you are automatically, this set of algebra will automatically give you 0. For example, this alpha is 1, then the square root, that's why you can see why this square root is important. This square root factor will automatically kill whatever state behind right? So it basically leads to a 0. And there's the same idea applies to the annihilation operator. If you try to annihilate on a 0 state, then you can't do that. So that also gives you 0. But if you try to annihilate on a single particle state, then basically you want to extract alpha from the states, right? So you first check by making this scalar product, compare them, and then alpha and alpha scalar product is 1. But after factoring out this scalar product, there's nothing left over, right? So you are left over with a tensor factor, identity of the tensor, and then which interpret as a vacuum state. So that's why, that explains why this fermion creation and annihilation operator has this form. And then also, the fermion also has the same property, which maybe we can talk about this next time. Thank you.